Hello, I'm Desiree Black, part of the team Practical Neurons. Deep convolutional neural networks has many artificial intelligence applications, but its model side and computational costs has stopped deployment on low power and resource limited embedded systems. Our goal is to reduce the bandwidth of the whole network to ternary values, which will greatly reduce model size, computational costs, and accuracy degradation caused by compression.
David Perez here. Our next step in our project is to create, configure, and optimize our dot product hardware in Verilog. The FPGA will load the weights from our neural network from an SD card and will store this data into the FPGA's ROM. Also, we will write code to read these values from ROM. At the current moment, our plan is to display the output with the 7-segment display. We are looking at alternatives like the VGA output, but the 7-segment display would be the most economical choice for our project. We are also confident that at the end of the semester, we'll be able to demo the image classification on our FPGA using our neural network. Thank you for your attention.
Hey, I'm Tejas, and here's a quick update on what I've been working on in the past few weeks. So basically, I've been making a hardware block diagram for the hardware path that we're going to implement into FPGA. And this is the hardware path for an 8-bit floating point number, which is the quantized version of the original 32-bit that TensorFlow uses. So basically, it is just a hardware block diagram, meaning where's the data coming from, what type of memory block is it going to, where the read-write path's going, and then the other blocks as well, like a multiply add block and a shifting block. And one other thing I've been doing is seeing the trade-offs between delay speeds and amount of hardware used. So we have to make a decision there on how much hardware we want to use and how much delay we're comfortable with.
Hi, I'm James, and I will be talking about the speed of this system. So we will have the inputs. These numbers will be inputs, like a single number will be a single input. We'll have to load them in. We'll have to compute everything, such as multiplication of the neural network weights, as well as adding the biases. We'll compute, that'll spit out an array of numbers. We'll figure out the maximum number and then scale as needed. And we'll figure out the final result of the classification of each of these numbers. So this is a 0, 1, 2, 3, etc. So all of these clock cycles add up to about 1,363 cycles. And our FPGA board has a clock of 50 megahertz. This means the speed per image is 272.6 microseconds. So for about 70,000 images, it'll take less than 2 seconds. And 70,000 images is about equivalent to a little bit less than 39 minutes of footage, assuming that the footage is 30 frames per second, which is pretty standard. So 39 minutes of footage, and it's all processed and classified in less than 2 seconds. I think that's pretty fast.